Welcome back to Spring Into Math 8. We're looking at Chapter 8, Part 2 review of a whole chapter. Now the fourth topic we mentioned in this chapter was linear equations and solving them by using substitution. So let's take a look at that. So the first set of equations we're going to look at as a review is 3x plus y equals 1. And our second equation is 2x plus 5y equals 18. Now we're going to use this special method to solve. So to begin, solve one of those equations so it equals y equals something. And in this case, we chose the first equation, 3x plus y equals 1. Now we're going to do some rearranging or some moving of some things in order to make it say y equals. So we're going to go ahead and subtract 3x from both sides of our equation in order to keep it nice and balanced. So our new equation now reads y equals 1 minus 3x. This is the perfect form that we want to have it in and makes it much easier to work with. So we say that y is worth 1 minus 3x. We're going to take that and substitute it in for the value of y at our next equation. So our first equation, the original one, looked like 2x plus 5y equals 18. And we're substituting that value we found for y, 1 minus 3x, in for the variable y. And to do that, we stick it inside a set of parentheses. So we have 2x plus 5, parenthesis, 1 minus 3x, close your set of parentheses, equals 18. The first thing we should do in order to help us solve this equation for x is to use what's called the distributive property. I'm taking the 5 on the outside of the parenthesis and multiplying it by both things that are inside that set of parentheses. And this is what it looks like. 2x plus 5 minus 15x equals 18. Now, we're going to combine some like terms here. We have 2x's and negative 15x's. If I add those two together, you can see here in red below we have negative 13x plus 5 equals 18. Now, I need to get that plus 5 moved to the other side of my equation, and to do so, because it's positive, we must use subtraction to do so. So we've subtracted 5 from both sides here, and I've shown you that there in that color red. And once I subtract 5 from both sides, my equation now reads negative 13x equals 13. And then we can divide both sides of our equation by negative 13, so that negative 13 drops off from that value that's attached to that variable x. And when we divide, we get the answer x equals negative 1. So now that we have x value, we can go ahead and stick that back into our original equation of y equals 1 minus 3x, the one that we rewrote earlier. And instead of putting that variable x in there, I'm going to drop a set of parentheses in there and put that number, negative 1. And then we're going to use the distributive property a second time to help us solve what the value of y will be. So you can see here I set it up like y equals 1 minus 3 and put that negative 1 in parentheses. Now, negative 3 times negative 1 actually gives us a positive 3. Negative times a negative is always a positive. So then we simplify. We have y equals 1 plus 3. And we all know that 1 plus 3 equals 4. So the value in this case for y is 4. So we pull that x value we learned earlier, which was negative 1. We stick that in a set of parentheses, drop a comma down, and put the value for y, which is positive 4, and we wrap those parentheses nice and close. So this is the exact coordinate if we were to graph those two equations, where those two lines would cross on a coordinate plane. Topic 5, solving linear equations by using the elimination method. A 2-by-2 system of linear equations can be solved algebraically by the elimination method. But in order for us to use this method, we must write an equivalent system of equations, such that when two of the equations are added or subtracted, that one of the variables is limited, either the x variable or the y variable. And we're going to see what that looks like right now. So here's my example. 3y equals 2x minus 5. And then my other equation is 2x equals y plus 3. Now we need to rewrite this in a more friendly way so we can see that when we add or subtract these equations that the x values or the y values go away. Now I'm going to set mine up so that it sees here at the bottom I have negative 2x right over a positive 2x. Now if I were to add those two equations together, the x values would go away and it would look like this. So here we've eliminated the x variable, and negative 2 plus positive 2 is just 0. 3y minus y gives us our new 2y, and negative 5 plus 3 gives us negative 2. So our equation currently as it sits reads 2y equals negative 2. And we're going to go ahead and simplify and solve for y, and in this case we divide both sides by 2, which results us in getting the value of negative 1 for the value of y. So we just learned that the value of y in the system of equations is worth negative 1. Now we're going to take that value and insert it into one of the original equations so we can get the value for x to see where these two equations would cross on a coordinate plane if we graph them. So here we go. 2x minus y equals 3. So instead of putting that y there, I'm going to drop a set of parentheses and put that negative 1 in there. It's shown there in red. So it now reads 2x minus negative 1 equals 5. Now, a negative times a negative turns that negative 1 into a positive 1. So we have 2x plus 1 equals 5. We're going to go ahead and subtract that from both sides of our equation. So we have 2x plus 1 minus 1 equals 3 minus 1. So we have had 2x equals 2. We divide both sides of that equation by that number 2, which is in front of the variable of x, and we find out that our x value is worth 1. The solution to this set of equations is the coordinate 1, negative 1. That shows us on a graph precisely where they cross. Topic 6, solving special systems of linear equations. We'll kind of go backtrack a little bit here. Remember earlier we talked about 3 different types of solutions that can happen when solving a linear equation or a system of linear equations. We have a one solution answer, which is exactly what we've been talking about when graphing equations where they cross. That's one of the most common situations that you'll see working in this chapter. Now we also talked about what a no solution would be. And an example of that would be 2 lines that are graphed and they're parallel, which means they never ever intersect. So there would be no solution to those types of equations. And then lastly, we have infinite many solutions. This means that the same line is graphed twice, and those lines sit right on top of each other. So you actually, when you graph those 2 equations, you're actually only getting 1 line on your graph. That means that we have infinite number of solutions. That's it for Chapter 8 review. I hope you learned something fun. Next chapter coming up is the topic of functions. See you later.